Okay, so we're given an integer array nums with these numbers and we want to get the XOR of all of these numbers, and we want to count the minimum operations we need to flip the bits in order for it to equal to our given k. First, we need an observation. So this is the XOR truth table. We see that with bit A and bit B, if we flip either one of the two bits, the result is gonna change from either 0 to 1 or 1 to 0, right? Because as you can see here, this is 0 and 1, right? So if I flip this to 1, it's 1, 1, and it's gonna change from 1 to 0, right? It's the same with B. With 1, if you flip it to 0, it will become 0 and 0, and the output will flip from 1 to 0. This is also the same as this situation, as this case. And this 0, 0, if we flip either one of the two bits, it's gonna be 1, right? And this is the same. If we flip either 1 to 0 or this 1 to 0, but not both, right? We need to flip 1 at most. We cannot flip twice. We only need to flip 1 of those two. Okay, so 1, 1. If this changes to 0, then it will become this. Okay, if this changes to 0, it will become this. So 0 to 1, right? So with this important observation, and as you can see, I use a software called Logisim, and it basically simulates everything that we talked about. As you can see, if we change one of the bits, right? If we change one of the bits, the result will be flipped. The result is always going to be flipped. Whatever the bits are, the result is going to be flipped. That is definitely going to happen. So with our case here, we can see that this is like I've converted these into their binary representation. As you can see here in this column, as the observation we just saw, is that if we flip one bit, the result will flip itself, right? So in this case, if I see here, in this column, I don't even care if this is 0, this is 1, or this is 0. I don't even care what other zeros and ones are. I only need to know that if I flip one of these, the result will flip itself, right? That's an important observation. And it's the same with the remaining column. It's the same, and this column also, it's the same. We have two things here. So with each of these columns, we can see that we can either flip one of these to flip the result, okay, to flip the result. So it will take one operation, and we don't flip anything, so it stays the same. Just don't do anything, it stays the same. So it took 0 operations. So you can see that with each of the column, we take one operation at most. So as I said before, if we flip one of these bits in the same column, the result will be flipped. And that takes us to another crucial intuition, is that the number of total operations we need to take is the number of bits we need to flip to make the result, like the number of bits of the result we need to flip to make it equal to k. Okay, so with this we can see that okay, the XOR result of this column is 0, XOR result of this column is also 0, and the XOR result of this column is 1. Okay, and k we have here is the example 1 in the description. We have k equals to 1, right? So this is k, this is k. Okay, so and this is our result. So how many bits do we need to flip to make the result equal to k? We need to flip 2, right? Because you see in this column the bits are not the same, so we need to flip, right? We need to flip. In this column the numbers are the same, so we don't need to do anything. This column stays the same, this column stays the same, right? And in this column we flip from 0 to 1. That means we have to flip one of these. We have to flip either 1 to 0 or 0 to 1 or 1 to 0, 1 to 0, 0 to 1. We just need and we must flip at most one of these. We cannot flip 0 to 1 and then 1 to 0. We cannot do that. We cannot do 2, right? We can only do 1. We can only do 0 to 1, or we don't change this and we change 1 to 0. Okay, so just flip one of these. This is at most 1, at most 1. This is very important, right? And this is the same. We need to flip 1 to 0. So this is the same. We need to flip one of these. We need to flip from 0 to 1, or 0 to 1, or 0 to 1, or this 1 to 0. Okay, we can see that the min number of operations needed is the number of bits that are different from result compared to k, right? We see that okay, result and k both have 3 bits, but with result and k they only have one column that are the same, which is the middle column. They are on 0 and 0, so we don't need anything. We don't need to care about that. But with this column, this is 0 and this is 1, so we need to take one operation here, and this is also different from 1 to 0. We need to have plus 1 operation here, so the total is 2 operations for this. How can we count the number of different bits between result and k? How can we do that? We do another XOR, right? XOR, because XOR tells you like XOR only outputs 1 if 2 bits are different, right? Look at this. It only outputs 1 if 2 bits are different. 0, 1, 1, 0. It outputs 0 if these two are the same, these two are the same. So that actually is what we are looking for. We are looking for an indication of how can we find the number of differences between the result and k. So with the result here, we need to XOR with k to find the number of operations we need to make. So let me rewrite this. So result is 100, right? And k is 001. 1. So, and the XOR of this 0 1, it's 1 0 0, it's 0 1 0, it's 1. So this is the XOR of that. And we see that we have two number ones, right? So what do these dictate? They dictate the number of operations we need to make, right? Because we see it only outputs 1 if 2 bits are different. So the number of ones we see in our result is the number of different bits between the result and k, and these number ones, the number of ones we see in this is our final result. Okay, our final result. At first, in terms of speaking, I can say that the step 1 is that we find the XOR of all of these numbers in the array as we did, and the second step is that we will XOR the result that we get from this XOR, and we will XOR that result with k. But with step 1 and step 2, we can actually shorten into one step, is that we will XOR everything. So what I do here is that I will scan through all the numbers in nums. I will scan through 2 1 3 4, and then I will XOR that with k. This is the accumulated XOR sign. And then when I get everything, and when I get this, right, if I XOR k with all of the numbers in the array, I'll get this. So eventually k becomes this in my code, and I will turn k into a binary representation. So this function here, this function bin here, is actually gonna convert k into its binary representation, and I will count the number of ones in that, and I'll return that. Because why we have to count the number of ones? Because as we see here, the number of ones indicate the number of different bits between this and this, right? So that's what we want to do. That's pretty much it.